denoted as x sub I, px equals xi, okay, or you can also call it p of xi. Okay, these all mean the same thing. So what we're saying is that we have a set of messages, and I'm going to just define the set of messages to have, so we can think of a probability mass function which looks like this. This is the message 1, this is message 2, this is message 3, and so on until some message n. So that's a set of messages. And then on the y-axis I had the probability, okay, and let's, if I'm going to call message 1 x1, message 2 is x2, message 3 is x3, etc. until xn. And then on the y-axis I have the probability, okay, this is probability that the random variable x equals x1, this is probability x equals x2, all the way on probability x equals xn. And this is a probability mass function of a discrete random variable, as we saw last week. Okay, there's nothing new here, but it essentially allows us to now start using random variables as opposed to dealing with message sets. We can go from sets to variables, and the implicit assumption here, of course, is that the messages are discrete. Okay, we have a certain finite countable set of messages, or even if it's infinite, it's countable anyway, and we have associated with these discrete values, discrete messages, discrete probabilities, and so we can talk about probability mass function or distribution. And so from now on, we don't need to talk about messages anymore. Okay, we just say random variable x represents the messages, and we know that the values assumed by this random variable, okay, arise from some underlying sample space and some underlying outcomes and some underlying distributions, etc. But we can just deal with random variables from now on, which is why I wanted to spend a lot of time last week on random variables, because this is exactly how information theory uses random variables. So we now view, if you take a billboard and you walk past it, what we're saying is that there's some random variable, say b for billboard, and the message on the billboard is b equals one of these messages. Okay, and so we see the value of the billboard, but that's some random variable taking on the value of the billboard. Okay, so we're kind of going into this random variable as opposed to the actual communication we're off in this random variable space. Okay, so that's a important methodological step for us to take, because now we're going to go into random variables and we can use all the results from random variables from there. So using that now, we can define the entropy even more simply like this. We'll say that if we have a random variable x, which is a discrete random variable, etc., then we have some underlying distribution probability x equals xi. Now in the book, in the text, I'm using capital P for probability. Information theory textbooks use capital P for probability, but in the probability chapter I decided to use small p for random variables and capital P for events, and now I'm kind of stuck. I don't know which way to go. Either I can be consistent with information theory books and use large P, or I can use be consistent with myself and use small p. So here I use capital P, but just to be consistent with last week, wherever you see capital P, just it's the same as small p, which is why I put that note on Piazza. Okay. But at any rate, we have some random variable x, we have some underlying probability mass function, px equals xi, and then we can define the entropy of x to be equal to, and we just use the notation sigma x, which means that the sum over all the x sub I in the domain. Okay, so x sub I belongs to D, where D is the domain of random variable, and we just say p x I, or I guess we call, what is the exact thing I'm using here? I think px, yeah, log p xi. Okay, so this is the standard definition that you will find in any textbook on information theory, where the sum of x is a shorthand for sum over all the discrete values in the domain. Okay, xi belongs to D, where D is the domain of the random variable x. Okay, so to go back to the billboard, what we really need to know is that you, as a recipient, need to know the space of all possible billboard messages, of all possible advertisements. Okay, and that's kind of crazy. Okay, it's kind of crazy. How do you know it's going to happen? And so what we'll do is that in a few minutes we will see how to overcome that restriction. In the meantime, I'm going to show you a few examples to hopefully set the ideas. So the first one is, we have this notion of equiprobable messages. So I think we have in the book. This is a classic example in distributed computing. We have, how many people have seen this before? The communicating generals problem. You have these there are two hills, and there's general G1 here and general G2 here, and they're going to attack some army in the valley. Okay, and they want to send a message which says either attack at dawn the next day or don't attack at dawn the next day. So how many people have seen this before? Okay, so anybody who studied Byzantine agreement has probably seen this, or even if you studied basic computer networking, you've seen this. So I just put this in just for fun. So the way this works is that the previous night, the general G1, let me see how well I can draw this, sends a carrier pigeon. There, it's a nice tail, and there's the other wing. So okay, it sends a carrier pigeon from one to the other, saying either attack at dawn or don't attack at dawn. So from the general 2's perspective, think of it this way. We have, general 2 doesn't know what general 1 is sending. Either it's going to be attack at dawn or not, and let's assume they're equiprobable. If they're equiprobable, then what this bird is going to send is going to be just one message. So we have the random variable x takes on two values. x1 is attack at dawn, and x2 equals don't attack. And so we have the h is going to be, since the equiprobable is just going to be log base 2 of 2, which is 1. So essentially the bird is carrying one bit of information. Okay, so that's how we get one bit of information from this. So we can think of the bird as carrying the message 0 or the message 1. Okay, so it's sort of the simplest possible communication. Any question here? No. Okay. So what happens if the bird carried that message, but the general 2 had a prior expectation of what was going to be sent? Okay. So in other words, the messages were not equiprobable. Okay, so if the messages are not equiprobable, then actually we have a different solution. Okay, so let's think about it like this. Let's say that general 2 and general 1 are both observing the army down below. Okay, and they both have their telescopes and they can both see the army, so they both reach the conclusion, almost always the same conclusion. All right, but the general 1 sends a message anyway. However, general 2 knows the message that's going to come from general 1 with pretty high probability. Okay, so let's see what I mean by that. So let's say with probability p, the message is going to be 0, and with probability 1 minus p, the message is going to be 1. Okay, and so general 2 knows this. Okay, so even if general 2, when it gets the message, is going to be not that surprised. It says, yeah, I knew it was going to be attack at dawn because I came to the same conclusion, right? Because so if that happens, if the probability of that message, okay, which can be viewed as probability of general 1 sending it or general 2's prior expectation of the message, you can view it either way. Okay, but if either way the message is not that is not giving you much content, then the entropy will be lower. Okay, and the way to look at it is to look at this interesting graph over here, where on the x-axis we are plotting p, the probability of the message over here, and on the y-axis is h. And what we find is that it looks something like this. Okay, this is 1, this is 0, and over here this one is 1. I believe. So yeah, it's 1, and at 0.5. So it's probably hard to read. Okay, set 1 is over here. So what we read is like this: if the bird always carries message 0, Okay? Okay, so the probability of message equals 0 is, so it always carries message 1, so the probability that message equals 0 is 0, it's always 1. When the bird arrives to the other general, it didn't learn anything, you know, because if the bird is always carrying the message 0, which means attack, okay, this is equal to 0. It always says attack. General 2 says, yeah, you know, this other guy always wants to attack. You know, I didn't learn anything. You know, I expected him to say attack. He said attack. Big deal, right? No information was gained, right? On the other hand, if General 1 always says don't attack, this General 2 says that guy's a wimp. He always says don't attack. Okay, I didn't learn anything either. So that would be this case over here. The communication is maximized. We can think of the communication being maximized. We can think of the message having the most impact. You know, again, these are intuitive understandings of the system. When General 2 and General 2 has no expectation on General 1 other than, you know, I don't know, maybe with 50% probability he's going to say attack, 50% probability don't attack. So, you know, at that point the bird is getting the most information. Okay. So if one were to shoot down the bird, okay, when it had been sending this message with this probability, actually nothing would happen. There's no change in the system. Whereas if the bird was carrying a message and the prior set was 0.5, that would have the most information. Okay, so that's where we get this graph over here of P1. Okay, any questions about this over here? So this notion of having the entropy being defined in this way, okay, as sigma px log px, therefore can be made to be reconciled with our own kind of intuitive understanding of this simple system over here, and this can be generalized. Okay, we can have more messages, more generals, and, you know, more choices, etc. But the same intuition applies as we go forward. Okay, any questions about this here? Okay, let me do one more case, and then we'll take a short break. The other case is for a set of messages with a particular probability distribution, and I guess I'll do the homework over here because I managed to mess that one up again. Oh, where did I put it? I knew I put it. Oh well, I'll just tell you what the answer is, or I'll tell you what the answer should have been. So here we had two random variables, x and y, and x had some probability distribution, which whatever it is, and this had some other distribution. And I've asked you for the distribution of the entropy of x plus y. Okay, so first of all, it turns out that what I really meant to say was what's the entropy of x, y, the joint distribution of x and y, not this. So if you guys solved h of x plus y, you would have actually gotten the wrong thing, because it turns out h of x plus y is very complicated. I found a paper on on this, and all you can do is to do an upper bound. H of x plus y is a very difficult thing to compute. So if you computed it, it was wrong. Okay, pretty sure of that, unless you're advanced information theorists. So what I really meant to say was h of x plus x, y, and I said x and y independent, in which case it's h of x plus h of y. So that's the result. So the joint distribution, the entropy of the joint distribution is the sum of the entropies if they're independent. And the reason is because we send message x, we send message y, they're completely independent. So, you know, the total information gain is what you got from the first one followed by what you got from the second one, right? I mean, because the independent doesn't really matter that you got the first one, okay? If they are, even if they're independent, the sum is still kind of complicated. Just like the distribution of the sum of two random variables actually is the convolution of the individual distributions. In the same way, the entropy of the sum is non-trivial. Anyway, so for h of x, you just do the obvious thing, which is sum over x, you know, pxi log pxi plus whatever sum over y, pyi log pyi. And the answer is, can somebody give me the answer? I forgot to bring my sheet with me here. Did anybody solve this? 4.27 is the magic answer. Thank you. Okay, so if you got 4.27, assuming you did x plus y, if you didn't do it because you said the sum is not defined, that's a valid answer also. And you can blame me for that. Okay, and I'm sorry about that. Okay, so the point is that the entropies of independent variables, the joint distribution is additive, and that's sort of the basic result over here that I wanted to get across. So one of the things that always confused me about information theory, and no doubt if you haven't studied information theory before, might confuse you, but you won't be confused because I'm telling you how it works. But what might confuse you is that, okay, we say that x is a random variable that represents a message source, and this corresponds to some set of distributions of x1, xn, let's say it's finite, and we have some probability mass function px1, etc. to pxn. And most books, after they give the initial kind of description of messages and generals and so on, they say, yeah, and by the way, we're going to represent a message source by x, and we're done. Okay, done. That's it. Okay, x is being generated from some ergodic Markov process. So, okay, life is great. But you think for a moment and you say, this doesn't make any sense. And the reason it doesn't make sense is because we're assuming that the set of messages coming from the source are innumerable, and not only that, the recipient needs to know what are the associated probabilities. But if you think about it, we really don't know what the messages are coming from, let's say, a billboard. Okay, I take a billboard and I draw something on it. It could be anything, right? If I take this blackboard, I could draw anything I wanted on it, right? So how can you say that the number of messages is finite and innumerable in this fashion? It doesn't make any sense, right? So to take a more, let's say I draw a square on the board like so, and I just draw some scribble over here, that's a message, okay? And if I draw something else, that's another message, and so on. But I could have potentially an infinite number of messages. I could have another message that looks like this, or I could have message that looks like that. So if I said this message is x, how could I enumerate it? It doesn't seem to make any sense. So what's going on is that under the covers, we are doing a transformation. Okay, we're doing a transformation by going from messages to symbols. Okay, and unfortunately, no book I read actually talks about this. It's just kind of assumed that you know what you're doing. Okay, and so that's why I wanted to spend some time getting this across to you, which is that really what we're doing is taking this infinite space of messages and collapsing it down through a process of digitization. Okay, what we're doing is we're saying, okay, you can draw whatever you want. Okay, so fine. Let's say you draw some random squiggle over here. Okay, I'm going to draw some random squiggle. That's my message. But I'm going to be able to send this message by doing the following trick. I'm going to choose a very fine grid, like so. Okay, and I'm not drawing all of it. Okay, and so if I draw a grid like this, and if it's sufficiently fine, okay, sufficiently fine meaning that I'm sampling it faster than the Nyquist rate. Okay, so I haven't told you about the two-dimensional Fourier transform, but it's a generalization of the Fourier transform that allows us to take a spatial function. So taking a function like this, which is a function of time, I can take a function of two-dimensional space and compute the Fourier coefficients, and I can compute the energy at different Airy harmonics. So if I have a squiggle which is like this, it has less energy at higher harmonics than a squiggle like that. Okay, because as you can see, this one has a lot more kind of noisy, sharp behavior. This is a bit more gentle. Okay, so that's the intuitive understanding of two-dimensional Fourier transform. So if I sample it spatially at a fine enough grid, okay, for the sake of argument, I can certainly take this and do a sampling every micrometer. Okay, every micron I'm going to find whether there's chalk there or not. Okay. And I can argue that if I do that, I have a certain very large but certainly innumerable number of microns. Let's say I have, so 1 micron means I have 10 to the 6 in 1 meter. So this is about a third of a meter. So I have basically like approximately 10 to the 5 microns, 10 to the 5. So if I tell you 10 to the 10 values, okay, that's all the messages you could possibly have. If you have 10 to the 10 different values, that's going to tell me every possible chalk drawing, okay, roughly 10 to the 10, every possible chalk drawing, I can send it to you. Okay. So, though at first glance it looks like I have an infinite number of values, in practice I can always find sufficiently fine encoding over here. Okay. So, I have a 10 to the 10, and you think, oh, this is a lot, except that, you know, if I have one of, so I'm sending you 10 to the 10 different values, it's 10 gigabytes, okay, or 10 gigabits of information, okay, because I'm just sending you, is there chalk or no chalk, so this is 1 bit for each. So 10 gigabits, it's about 1.25 gigabytes, okay, and so I can put that in a thumb drive, okay, a small drive, and that's every possible, one thumb drive corresponds to one message. No matter what the message is, I can send it to you in 1 gigabyte. By the way, this is not a particularly surprising result. I can also take a camera and take a photograph of this, right, and send you a photograph. Right? The photograph is what, a couple of meg, okay, and so the camera is doing exactly the same thing. It's digitizing this image over here. And what happens with the camera is that each pixel position, I have basically got a grid location, XY location, and then corresponding XY location, I have whether there's chalk or no chalk. Okay, there's 0 or 1. And then I can send this message, and no matter what I draw, I can send it to you. Right? It's like a fax. So the fax is also doing. You draw whatever you want, send it in a fax, and the other side just prints out the image position. So while the space of possible messages is infinite, if you digitize it and you convert it into symbols, okay, because each thing I'm sending is a symbol, the space of symbols is finite. Okay, so messages, they are infinite, okay, but they can be represented by a sequence of symbols. So this is the transformation that we're going to do over here, which is converted to a sequence of symbols. And then what we can do is, instead of looking at the message frequencies, we can look at symbol frequencies. And that makes life much, much easier. Again, to take a simple example, the set of all possible books that have been written from now or in the future, unknown, right? It's infinite. I mean, we have no way of bounding that. But we kind of can bound it, right? Because if you think about it, let's say the number of each book has less than, let's say, 10,000 pages. Okay, it's unlikely to have a book more than 10,000 pages. Each page has maybe, I don't know, 1,000 symbols. So it's 10 to the 4 times 10 to the 3 symbols. Okay, and that's 10 to the 7 symbols. And then, you know, we can just look at, so if there are 26 letters plus uppercase under 26, and let's throw in all the punctuation, so up to 100 letters, so 10 to the 2. So I have basically 10 to the 7 times 10 to the 2 symbols. So 2 to the power 10 to the 9 is the total number of books can ever be written. It's finite. Okay, it's a lot of books, 2 to the power 10 to the 9, but it's finite. So in this set of books, finding the message frequency, by message I mean a particular book, is kind of hard, but I can do the following. It's only 100 symbols. There's only 100 symbols. I can find out the frequency of individual symbols. I can find out the frequency of the letter E, the letter A, the semicolon, the colon, the capital A, capital C, whatever, right? So each of these symbols that I'm using in the book, I can certainly find their frequency. And if I look at the total number of characters in a book, in a representative set of books, so I go to the Davis Central Library, I take all the books, and I just find out how many times the letter E shows up, and how much capital E shows up, and how much the punctuation this shows up, how much the integral sign shows up, etc. And I divide it, okay, by the total number n, okay. So this is basically the probability of the letter small e. I can find the probability letter capital E, probability semicolon, probability integral sign, etc. in this fashion, and therefore I get exactly what I wanted, which is the set of messages, but these are not going to be messages anymore, these are symbols. And I can find the probability of the symbol. So the general path is we take of all possible messages, you find a representative sample. Again, that same word, representative. So we just say this is representative, and we argue that's representative. And then we compute the symbol frequencies, and that gives us, to first approximation, some random variable x, which is at least the symbols, okay? But these are not the message frequencies. The message frequencies are, messages are made of symbol sequences. So again, let's think of it for just a moment. Certainly I can find the probability of Q, okay, as some probability, and this over n, so this is the number of occurrences of letter Q in all the books in the Davis library. I can say that's the probability of the letter Q, okay? That kind of makes sense. It's a symbol frequency, single probability. I can similarly find the probability of U. However, if I take the message, just a 2 symbol message QU, that's very, very likely, okay? It's almost impossible to find, let's say, QA or QB or whatever. These are all probability 0. Whereas if they're independent, the probability of QA should be probability of Q multiplied by probability of A, right? So if they're independent, the probability of a sequence of 2 symbols should be just the product. Whereas, as you can see right away, that's not the case. Okay, with Q, there are 2 symbols, which is often called the diagram frequencies are going to be very biased, okay? And so, however, even though the diagram frequencies are complicated, we could assume we could look at all diagrams and look at the probability of diagrams. You can look at the probability of trigrams. You can look at the probability of 4 grams and 5 grams and n grams, and look at the probability of all sequences of symbols of, let's say, length 10,000. Okay, if every sentence is going to be shorter than 10,000 symbols, then that 10,000 symbols, okay, which is 100 to the power 10,000 possibilities, right? 100 per 10,000 possibilities. I could hypothetically compute each of those, and that will tell me the probability of each and every sentence in the English language, okay, in that corpus, okay, and that gives me again xi, pxi, okay. So at least in principle, it's possible for us to compute it. The main message here is that first we have to go from messages to symbols. We can't just look at messages, okay. And second, once we get the symbols, what we do is we want to look at the limiting case of the probabilities of longer and longer symbol sequences, and when we do that, we'll find the probability, or I should say, we'll find the probability of each such message sequence and underlying probability here. And with this, of course, we can find h of x. Okay, if you get this, then certainly h of x is trivial to compute. So which brings me to the homework problem. So there I said human speech, which is some waveform, can be encoded as one of basically 64 different levels. Let's assume we're going to encode it. So suppose somebody told you, I'm going to have, all possible things that are ever going to be said or have been said in infinite future or past. Okay, what's the entropy of that? Okay, well, that's a tall message, tall order to deliver. But if I could to take the human voice and say, okay, voice for me is just this waveform, and I'm going to tell you there are only 64 amplitudes. So they're basically 64 symbols which correspond to this. Okay. So then what I'm going to do is that at each point in time, I'm going to say this corresponds to symbol, let's say 1, this corresponds to symbol 2, this corresponds to symbol 37, this symbol 34, whatever. And so I have a sequence of symbols. Okay. Then I can compute the probability of each symbol, okay, individually in some representative set of voices. So I can go to YouTube, download all the audio clips, and say this is the probability that symbol number 3 was being spoken. Okay, this by itself is not particularly meaningful, but then what we can do is we can start looking at 2 symbols together, okay, or 3 symbols together. So what's the probability of 3 different symbols? Well, we have 64 symbols, so we have 64 to the 3 of 3 sets of symbols. Okay, and then we can look at the probability of each of those 3 symbols over 64 cubed. That gives you the probability of that. And then we can look at 4 and 5 and so on. So the general rule is that if we can find, okay, I'm just going to read it out for you. So by identifying the underlying alphabet of symbols and computing the relative frequencies of longer and longer symbol sequences in a representative message corpus, we can approximately determine the source entropy, okay, because you can take the source, in this case, human speech, and compute the entropy of human speech by taking these symbols and taking longer and longer sequences. So we want to find out the probability of each such symbol sequence as we have more and more symbol sequences, and that is going to allow us to compute this over here, and hopefully it kind of converges, right? As we have longer symbol sequences, the entropy kind of settles down when it gets asymptotic entropy, and that would be the entropy of human speech. Okay. And so that's basically what I wanted you to think through the process. So the short answer is, we have 164 symbols. We compute the relative frequencies of symbol sequences in a representative corpus, and we take the limit of the entropy for these symbol sequences as the symbol sequence goes to infinity, and that allows us, in principle, to compute the entropy of human speech. Okay. So, any questions about that? Yeah. Okay. All right. So, what I tried to cover today is basically the intuitive basis for entropy and some examples over here. So from now on, we're just going to ignore messages and symbols and everything. It's just going to say, well, I have a random variable, and we're going to just work with the random variable, and we know the entropy of the source somehow, h of x, and this is sort of how we might go about doing it. In practice, this has been done for English like characters, and they find that the entropy is basically approximately 1 bit per English alphabet character. So each symbol, it goes anywhere from 0.6 to 1.1 to 1.2, depending on what corpus you use. It's approximately 1 bit of information per English character.